A guide to remote surveillance. Surveillance bugs, commonly known as covert listening devices, or simply bugs, remain one of the most effective tools in modern espionage and intelligence operations. These devices capture audio, and sometimes video or location data from targeted environments and transmit or record it for later analysis. In contemporary practice, bugs emphasize miniaturization, long operational life, remote access and resistance to detection, leveraging advancements in wireless technologies like GSM, 4G, 5G, Wi-Fi, Bluetooth, and low-power RF transmitters. This essay focuses primarily on the practical aspects of surveillance bugs, their current types, and technical specifications, methods for creation and improvisation, deployment, tactics, monitoring and exploitation strategies, countermeasures, operational considerations, and emerging trends. The discussion draws from ongoing developments in electronics, wireless protocols, and counter-surveillance tools to provide a detailed practical overview. Modern types of surveillance bugs and technical specifications. Today's surveillance bugs are categorized by their transmission method, power source, concealment strategy, and activation mode. Each type is designed to address specific operational requirements, balancing factors such as range, detectability, battery longevity, audio fidelity, and environmental resilience. 1. RF radio frequency transmitter bugs. These classic active bugs broadcast captured audio via radio waves, typically operating in VHF 30 to 300 MHz, UHF 300 MHz to 3 GHz, or SHF 3 to 30 GHz bands. Modern professional-grade RF bugs employ frequency hopping spread spectrum or direct sequence spread spectrum to make signals harder to intercept or locate. Key technical features: extremely small transmitters, often 1 to 5 cubic centimeters, or smaller high-sensitivity electret, or MEMS microphones, -40 to -60 decibels output power, adjustable from 5 to 100 milliwatts, effective range 50 to 500 meters, line of sight, extendable with directional antennas or relay nodes. Power is usually supplied by lithium coin cells, small lithium polymer batteries, or ultra-low power modes that extend life from days to weeks. Voice-operated recording activation conserves power by only transmitting when sound exceeds a threshold. Primary advantages: near instantaneous real-time monitoring, relatively low cost for basic models, and simplicity in short-range scenarios. Main limitations: continuous or frequent transmission produces detectable RF emissions, making them vulnerable to spectrum analyzers' direction, finding equipment, and broadband receivers. Advanced models mitigate this with very short burst transmissions, milliseconds to seconds, and pseudo-random frequency changes. 2. GSM, 4G, 5G cellular bugs. These devices operate like miniature autonomous cell phones, using a standard or custom SIM card to transmit audio over commercial mobile networks. Key technical features: compact size, frequently under 5 cubic centimeters, integrated high-sensitivity microphone support for voice-activated or always-on modes, battery life ranging from 5 to 60 days in continuous operation, and up to several months with voice-operated recording. Many models allow remote activation via incoming call-back listening SMS commands for configuration or app-based control. Some include GPS modules for location tracking or 4G, 5G data channels for higher quality audio or video streaming. Primary advantages: virtually unlimited range, wherever cellular coverage exists, no requirement for a nearby receiver, and the ability to blend into normal mobile traffic. Main limitations: dependence on cellular signal strength and coverage, potential traceability through carrier records, IMSI catchers, or abnormal SIM activity patterns. Professional versions incorporate encryption, randomized callback numbers, and low-power sleep modes. 3. Wi-Fi and Bluetooth bugs. These bugs connect to existing wireless networks or pair directly with a receiver. Key technical features: Wi-Fi models commonly based on ESP32 or similar system on chip operate on 2.4 GHz or 5 GHz bands with ranges of 30 to 100 meters indoors-outdoors. Bluetooth low-energy variants offer shorter range, 10 to 50 meters, but extremely low power consumption, often lasting months on a coin cell. Audio is either streamed live, buffered locally, or uploaded in bursts when connected. Many support WPA2, WPA3 encryption when joining networks. Primary advantages can masquerade as legitimate IoT traffic easy integration into smart home devices or public Wi-Fi environments and lower power draw compared to cellular options. Main limitations: limited effective range, without network access detectable via Wi-Fi scanning tools, ARP spoofing detection, or network monitoring software. 4. Hybrid specialized and emerging bug types. Audio-video combinations: miniature cameras with integrated microphones, transmitting compressed streams over 4G Wi-Fi or proprietary RF links. Laser optical bugs use a laser beam bounced off a window or reflective surface to detect minute vibrations caused by speech. No physical device needs to be placed inside the target room range, typically 100 to 500 meters. Body-worn wearable bugs concealed under clothing or in accessories for human intelligence collection, often with live transmission to a nearby handler. Passive reflection-based bugs: modern variants of Cold War-era resonators, activated only by an external interrogation signal. Contemporary bugs increasingly feature voice activation, AES 256 encryption, tamper detection, circuit self-destruct or wipe on opening, and anti-forensic design, no serial numbers, minimal metallic content, to evade nonlinear junction detectors. High-level techniques for creating and improvising bugs. While professional intelligence services procure bugs from specialized manufacturers, field operatives frequently improvise devices using commercially available components to maintain operational security and deniability. Essential components and assembly principles. Microphone: MEMS microphones 1 to 2 mm diameter are preferred for size and sensitivity. Transmission module: nRF24L0, 2.4 GHz low power RF SIM 800, LSIM 7600, GSM 4G or ESP32, Wi-Fi Bluetooth low energy. Power management: rechargeable lithium polymer batteries 100 to 1000 mAh, coin cells, or energy harvesting modules, vibration thermal or solar. Control logic: microcontrollers, Arduino Nano at Tiny or ESP32 handle voice operated recording, burst timing encryption, and command reception. Enclosure: 3D printed custom housings or repurposed everyday objects, USB chargers, smoke detectors, power strips, wall clocks. Practical improvisation approaches. 1. Bluetooth Wi-Fi modification: disassemble a wireless earbud or smart plug, extract the microphone and system on chip, reroute audio paths, and add a custom voice-operated recording circuit. Program the microcontroller to wake on sound, record briefly, and transmit in encrypted bursts. 2. GSM-based builds combine a SIM 800L module, tiny electret microphone, and small lithium polymer battery. Flash firmware to enable auto-answer on specific caller ID, SMS, remote control, and voice activation. 3. Passive cavity construction: build a resonant cavity using conductive foil, a flexible membrane, for example mylar, and a tuning capacitor. The device reflects and modulates an external RF beam only when interrogated, eliminating internal power needs. 4. Low signature enhancements: implement frequency hopping, spread spectrum via software-defined radio principles, use compressed audio codecs to shorten transmission time, and add randomized sleep intervals. 5. Testing protocols: use portable spectrum analyzers to verify emission profiles, environmental chambers to simulate temperature, humidity extremes, and audio playback tests to confirm clarity. Field improvisation kits typically include fine-tip soldering irons, multimeters, heat shrink tubing, epoxy for sealing, and pre-tested modules. The goal is rapid assembly with components that appear innocuous if discovered. Tactics for planting bugs undetected. Successful deployment depends on gaining access without arousing suspicion, achieving effective concealment, and leaving no forensic trace. Primary access methods. Social engineering pretexts pose as maintenance technicians, support delivery personnel, cleaning staff, or utility inspectors. Use forged credentials, uniforms, and believable cover stories to gain entry during business hours or scheduled visits. Bump and plant technique: brief deniable physical contact for example brushing past a target in a crowd to slip a small tracker or audio bug into a pocket bag or vehicle. Vehicle placement: attach magnetic or adhesive bugs under the chassis in wheel wells or inside door panels during valet service parking lots or brief unsupervised access. Gift or insertion: conceal devices in corporate gifts, for example desk clocks, USB hubs, picture frames, office supplies, or building fixtures during construction renovation phases. Concealment and placement techniques: everyday object integration: embed bugs inside power outlets, surge protectors, lamps, smoke alarms, air fresheners, plants, books, or computer peripherals. Structural insertion: drill tiny access holes 1 to 2 mm, insert via flexible probes and seal with color-matched epoxy or cork. Common locations include baseboards, HVAC vents, crown molding, and under carpets using heat to melt glue and slide devices beneath. Remote deployment: use small drones for aerial drops onto rooftops or window ledges, or launch projectile-based bugs with suction cups or adhesive darts. Operational best practices: timing and distraction: plant during high activity periods, meetings, parties, maintenance windows, when attention is diverted. Redundancy: deploy multiple devices in different locations and with different transmission types to ensure coverage if one is discovered. Forensic hygiene: wear gloves, avoid leaving DNA hair, use sterile tools and clean surfaces to remove fingerprints or tool marks. Strategies for monitoring and exploitation: monitoring infrastructure, receivers and control interfaces, dedicated handheld or laptop-based receivers for RF bugs, smartphone apps or web dashboards for GSM Wi-Fi models. Relay systems: deploy intermediate nodes, for example nearby vehicles or rented apartments, to extend range and obscure the final collection point. Activation protocols: use callback numbers, SMS commands, scheduled wake-ups or geofencing triggers to conserve power and reduce exposure. Intelligence exploitation: real-time analysis: feed audio streams into speech to text software, keyword alerting systems, and AI-based sentiment voice print analysis. Cross-referencing: combine bug-derived intelligence with open-source data, financial records, travel patterns, and human sources to build comprehensive target profiles. Psychological operations: introduce controlled disinformation through compromised channels to create distrust, misdirection, or internal conflict within the target organization. Data security: encrypt all feeds end-to-end, store recordings on air-gapped systems or encrypted cloud instances, and use secure deletion protocols after analysis. Countermeasures and technical surveillance countermeasures, TSCM. Core detection tools and methods: RF spectrum analyzers scan wide frequency bands 1 MHz to 10 GHz plus for unexpected signals carriers or modulation patterns. Nonlinear junction detectors detect semiconductor junctions in dormant or powered-off devices even when no signal is present. Thermal imaging cameras identify heat signatures from active batteries, processors, or transmitters. Lens finders optical detectors illuminate and detect reflections from camera lenses or hidden optics. Acoustic and physical inspection use endoscopes, borescopes, X-ray scanners, and manual probing to locate anomalies in walls, furniture, and fixtures. Comprehensive TSCM protocols conduct baseline RF scans before and after entry. Perform layered sweeps, broadband RF detection, nonlinear junction detector, sweeps, thermal checks, physical examination. Deploy white noise generators, RF jammers, where legally permitted, and acoustic masking devices during sensitive meetings. Establish secure conference rooms with soundproofing, RF shielding, and regular bug sweeps. Train personnel to recognize suspicious objects, unusual behavior, or signs of tampering. Defensive postures: assume all smart devices, phones, speakers, TVs are potential vectors and isolate or disable them in sensitive areas. Conduct periodic sweeps of offices, vehicles, and residences. Use decoy bugs or dummy devices to confuse adversaries and waste their resources. Operational considerations, risks, and emerging trends. Key operational factors: Risk versus reward bugs provide unparalleled insight, but carry high exposure risk if discovered compromised operations, diplomatic incidents, or legal consequences. Legal and ethical boundaries. In most jurisdictions, unauthorized bugging is a serious crime. Authorized use is tightly regulated. Adaptation to countermeasures. Continuously evolve transmission techniques, for example ultra-wideband optical data links, to stay ahead of detection tools. Emerging trends. AI-enhanced bugs with onboard edge processing for keyword detection and anomaly reporting. Nanoscale and bio-inspired devices, for example insect-scale platforms. Quantum-secure encryption and anti-forensic materials to defeat future detection methods. Integration with broader sensor networks, audio plus environmental plus motion data for richer intelligence pictures. Surveillance bugs continue to represent a powerful fusion of advanced electronics fieldcraft and strategic patience. Their effective use demands meticulous planning, technical proficiency, and constant vigilance against evolving countermeasures.